Yeah, thank you so much. I'm really pleased and honored to be here. And I'll do my best to keep the time. I'll skip a few slides. I try to focus on the important stuff. Yeah, thank you for allowing me to be here and giving this lecture. So I tried this lecture several times, and I hope it improved over time. It's also a little bit shorter, or it became shorter over time. And it went through a couple of titles. So the first title I used and tried it out with was, while machine learning is what you say, regression is what you do, mostly. That was somewhere in Texas at a small conference, and I made a big deal out of that. There is a founder of some startup technology company who got really famous with this tweet, where he essentially remarked that when you're fundraising, it's artificial intelligence. When you're hiring, it's machine learning. When you're implementing, it's still linear regression. And when you're debugging, if you're one of those programmers, it's still printf. So we do a lot of new things, but we also always reach out to use well-established methodologies in better understanding the data we are faced with. And my lecture today is about process data, which is in some ways a new type of data. It's certainly not something that hasn't been there at all. But there's a huge explosion around computer-based assessment and essentially logging everything a student is doing and trying to figure out whether that actually gives us any added value. So that's what I'm talking about today. But before that, there was the second title, where I tried to be funny again, not quite successful. The emperors came in because of a book that came out a long time ago, sometime in the 80s. It was called The Emperor's New Mind, and it was essentially making the case that it's not enough to build a complex enough system, throw a lot of data at it, and then something intelligent comes out. It needs a lot more than that. And when you look at some of the applications today, you sometimes see that there's an almost positivistic, maybe naive expectation that you just use something like IBM Watson. You throw whatever items at it. You take a bunch of mathematics items, throw it at Watson, and Watson will produce new items or magically tell you how to score them. Or magically, in my case here for this lecture, tell you how to interpret and utilize process data. Well, anyway, there were more books from that era. Can you guess what year this is from? This is an ETS edited book by Roy Friedel. If you know ETS and people there, you might guess based on the name what year this is from. So this was Artificial Intelligence, 1987, and the future of testing. So even back then, people were already talking about this. After the 80s, AI entered what it's called the artificial intelligence winter, because computers were not powerful enough. And I don't want to be unenthusiastic. That's usually, or mainly because that's maybe my cultural background, that I don't sound as enthusiastic. I actually play with those things, and I think they are very, very useful, but not for everything. So I've been playing with language models that can be used to generate text, that can be used to generate surprisingly real-sounding text, and you can apply and try out those things online. And you can actually have decent success to produce something that looks a lot like an item. Whether they are useful, of course, we still have to empirically test them, but we do the same with human-coded or human-generated items. So now my final title, what you always wanted to know about process data, but were afraid to ask. I couldn't come up with anything better, but that was essentially my journey with process data. I saw a lot of research going on there. I saw a lot of stuff happening around timing data, around action sequences. There was a lot of enthusiasm around, well, if we know the process data, we know what the students have in their mind when they solve those items, which I would be a little careful about. We have a lot more data, that is true. But they are often collected incidentally, and I've sat in a lot of meetings around how to make sense of process data. I was on a project called Big Data, funded by the National Science Foundation, between Columbia University, the Department of Statistics, ETS, and then me as an external advisor. And these data are really hard to make sense of, because usually they're made for programmers, and they are made for programmers to debug systems. They want to look at whether the computer-based test actually functions the way it's supposed to function. Very often they have timestamps for everything. Somehow that actually works good. They have timestamps for everything, so every action is logged in the process data. You have huge files with many, many lines that say, at this second, the following thing happens. There's an action that is logged, either a key press, a mouse click, opening a window, using a navigation bar, something like that. Sometimes we also have extensive additional process data. We might have eye tracking. We might even have people sitting in those magnetic resonance image producing devices that essentially completely enclose you, but you're still supposed to solve math items. You might even get physiological data, you might even have environmental data, etc. Today I will mainly be focusing on timestamps and actions, but this can be easily extended around other types of data. The question is, do we use all this stuff, or do we just ignore it and focus on what the assessment was built for? Do we only focus on what the experts tell us? Experts will also use process data to make inferences, whether a student has good understanding, full understanding. They might actually tell you in different domains what is expected at what point in time, what kind of explanations somebody should give, what kind of solution steps they should go through. So all that is in some ways also process data at a very high level, obviously. The ignoring part obviously won't happen because there are too many researchers interested in this kind of new data source. The use question is, well, how to use it and for what purpose? Should we include this in scoring? Should we include this as kind of secondary information to maybe find out about what type of strategy somebody's using? Maybe find out whether somebody was guessing, whether somebody was cheating. Test security might be a potential application. Many other things can be imagined. We can certainly learn from these new developments. However, I believe we need to overcome the hype cycle, so I think we need to become realistic in terms of what type of added value it can give us. There are new methods on the horizon, different new estimation methods, much more general latent variable models. We can use maybe AI, like deep learning approaches, language models, and we can certainly gain new knowledge. We just always have to reference it maybe against the old knowledge that we already have, or the types of things we would like to know more about. Because just using them in terms of exploratory data and finding out, well, there are patterns, there are differences, that alone I think is not enough to really gain, in some ways, a qualitative leap in terms of better understanding what students are actually doing, or whether they actually fully understand what we ask of them. We hope that process data is obviously this kind of missing link that we really help us to better understand, that we really better understand what students are doing. Hopefully we can also gain knowledge in terms of how to design better assessments, and that actually turned out to be true quite a bit in terms of just working in large-scale assessments and seeing what we can find out about how students interact with these items. I don't think we necessarily need a new psychometrics, but we can enrich the existing psychometric methods and put in those new tools and hopefully get better at understanding those types of data. Issues are certainly that we can still see that students will be smart entities interacting with items, even at the process data level. We can't look into their minds. We can only look into what they are doing. We are producing an interpretation, a narrative around that, what they are doing, but we can't really know what we label them with is actually happening in their minds. At the very simple level, the College Board had a little bit of an issue with a lot of test prep companies that were essentially telling students how to write good essays or essays that are tweaked so that they would get a higher score. You have to read more, you just have to use some persuasive techniques. You can do whatever, learn a few phrases that seem to be very nice and work well and don't really say a lot but make you sound really intelligent. All these things also apply to process data in a different way. So for example, there's research that says, well, rapid responses typically are caused by guessing or by not very engaged respondents. So what's easier than saying, well, let me find out what they consider a reasonable time to respond, and then I just wait, I count internally beyond those 5 seconds, and I only respond then. There are approaches called the rapid, what was it, Steve Weiss? Steve Weiss and colleagues worked on something where they had a model essentially that tried to eliminate those responses that were too fast, and then you would only count the responses that take long enough. So the easiest way to do is, if you see a hard item that you can solve, respond fast, because they won't count. Take a little longer with the easy items and respond to them potentially, hopefully correctly, so that way you can maximize your score. So there's also faking on process data. We won't be able to completely look into people's minds just based on process data. The hope is, of course, that we can gain more based on process data compared to only responses, by essentially seeing whether the responses always have error. If we want to minimize error, we can throw in all kinds of process data and hopefully get a better prediction of what students would be doing on the total test. We can aggregate over multiple items and we might actually gain something. We can also use process data to see whether the scores that a human might give based on, say, a holistic kind of scoring rule for a performance, whether that can actually be backed up in terms of what students are doing when they directly interact with a computer testing platform. So in the end, I'm kind of enthusiastic. I think we can do a lot. I think we just have to be somewhat careful in sharpening our tools and to find ways to better understand where process data really don't provide that much more, whereas in other cases we might find that process data is actually something that can tell us a lot more about students. We certainly need to mix old and new. We certainly try existing methods. There's a researcher at UPenn who is trying to find out whether students in gaming environments are, or in assessments as well, whether they try to essentially not quite cheat, but to get the easiest way out of the assessment, to spend minimum time in the assessment, to try to find out what's the easiest way to go through this thing in order to get a maximum outcome on the one hand, but on the other hand also not to spend a terrible lot of time at the assessment. So I have a couple of examples with me and I would like to show you a few. I will skip through the first one a little bit faster because that is really just the basic. The first one is about trying to find ways to predict what somebody actually will do at the final outcome. Will this person get the item right or not? And people have been working a lot on trying to predict this based on what students are doing during the solution process. One of the things that are typically done is, well, we look at whether speed and outcome actually correlate. do faster students get the items right? Do slower students get the items right? And the answer is, it depends. It depends on the item. It depends on whether it's a complex problem or an easy problem. So for complex problems, the faster students don't get the item right. For easier problems, the faster students get the item right. Are there process indicators? If people do a lot versus little, does that predict success? All these research questions usually are answered with pretty exploratory studies. So we throw in the whole kitchen sink of data we have, and we look at whether something comes out that predicts success. Standard operation procedure is usually correlations. We look at some form of a strategy trait or the ability estimate overall. We look at the task success for the same item, and we look at the log file data. If we only look at the same item and log file data, in some cases this problem really becomes trivial, because if you know whether somebody went through the steps in a math item, it's pretty trivial that this person will likely also answer the item correctly if all the steps are done correctly. At the other end, if those process data are just strategy differences, it's also trivial, because strategy differences can be more or less efficient, but not necessarily more or less successful. So that's an empirical question. We don't know that. But there's no reason to believe that necessarily, if given enough time, that 3 different strategies have to be differentially successful. They can be, but they don't have to be. Then the overall ability estimate as a strategy trait, that might also just give us very rough kind of predictors that are not very specific to the validity evidence we're looking for. So one of the things we tried to do was to aggregate up to come to somewhat more interesting features in that sense, that actually have to do something with theory, that has to do something with, for example, in some items, scientific inquiry being, or suggesting certain rules, being a guidance for how to solve simulation items. That went from the truly or fully exploratory stage to something that is a little bit more theory driven, and that will then hopefully better give us a better chance to succeed and to predict whether somebody is successful in the end. And it's hopefully also more generalizable. However, those theories very often simply don't exist. There are a couple of papers associated with that, but I would like, in order to keep moving and hopefully getting through the last few slides, move on so I can give you all the references I will send around the papers. We try to do a little bit more theory-driven stuff in the context of computer-based case studies at NBME, where we also try to focus not only on a single item, but also to go across items and to find something that is generalizable, hopefully, that gives us access to what types of actions and what types of strategies somebody takes in order to be successful on these types of exams. This came, of course, with a couple of issues just around testing medical students in itself is an issue. They tend to be really smart, they tend to be really good. So you don't have terrible amounts of response variance. But I think it was kind of an interesting study in the end, and we were successful in improving the prediction of success across multiple items. Again, just for the record, there's a lot of research going on around these computer-based case studies. This is more or less just the background reading around these types of items and how they are being used and how they've been developed. These computer-based case studies are pretty complex simulations. They tend to take 8 to 10 minutes. You get a history of a patient. You can do all kinds of things. You can do 2,000 different interventions, from giving aspirin to amputations or whatever. referring somebody to somebody else. You can wait for tests to come back. It's a very open environment. You can do essentially everything you might think of. Using task success as a criterion seems straightforward. Within each task, there are very specific actions that experts would say are the right thing or the wrong things to do. What turned out to be the case, unfortunately, because we have a highly selective sample, is that many of these very good predictors also were too good to be true, at least in this particular population. So they were essentially very easy for students to actually get right. So we had a hard time distinguishing between what makes a good problem solver versus what makes a less successful problem solver. So we will have not so obvious predictors only in really rare cases, and they are then usually also criteria that would say if a student doesn't get that usually means that something is really wrong and the student really didn't know what to do in this particular situation. There's also the problem of task specificity, that very often these cases are very specific to a subject domain in medicine, to a specific speciality. So there were all kinds of things that make these data less than an ideal testing situation. However, we had a lot of data, so we had at least 10 computer-based cases. These poor people are being treated to 10 cases that last about 1 hour each altogether, between seeing the patient and writing up the letter and deciding what to do. Sorry, that are the real patients. Here the computer-based cases are essentially a little bit shorter, but they are still doing a lot of time in front of the computer. Every solution requires a lot of actions. They have to find out what is wrong with the patient. They have to order some tests. They have to interpret the test. They have to wait. They have to order or make sure the test order and the between diagnosis and treatment is more or less sequenced correctly, that you wait long enough to see changes if you intervene with some things, that you advance time to see whether things actually happen. In the end, experts have to interpret what's going on, what's the correct solution, and if you ever worked with expert groups, if you put 2 expert groups together, one after the other, you will get 2 different solutions. So that same thing happened also with these cases. So we thought maybe a mechanical or psychometric approach might work a little bit better. Let me skip the next slide. Sorry, that one is out of order. That is just that overall the length of the system. We have 10 cases that are operational, 3 cases that are more or less pre-tested. Each of the cases then has associated actions with it that are considered beneficial, neutral, or wrong, essentially. Between these, there are several categories that are of no concern here. They can be organized in 9 subcategories, and each action is more or less recorded, whether it appeared at the right time. And then at the end, you get a relatively complex system that scores this based on human-generated, expert-generated scoring rules. We just did a basic aggregation of data, and we were already pretty successful. We essentially just said, well, all these items are way too easy for this very selective sample. We just produce a conjunctive scoring rule based on this highly aggregated process data and look at whether this aggregated scoring rule actually gives us a better solution. And it turned out that this binary score indeed was much more useful. We had fewer scores per case. We had more scoring variants. And just in very simple words, a conjunctive scoring rule that says, well, you have to have all these right in order to get this full credit, actually made those very easy items into a harder aggregate. So it's much harder to get everything right than to get a 90%, 95% chance to get each of them right. In the end, we put this into a rush model, and we were able to essentially improve over the previous approach. That didn't let us stop, because we had another summer student who came to us for 2 months, and we came up with a different type of scoring rule that is a little bit more truthful to the fact that we actually have a random process here. We have a full distribution of either using the wrong choices or finding the correct choices, and we essentially have count data. It's still a very easy, very skewed distribution, but you can use a beautiful model that it's heavily underutilized. It's called the Rush-Poisson counts model that can be used. I don't want to go into the equation. I promise that's the only equation in the whole lecture here. But that model was used, and we were able essentially to come up with a much better scoring rule. We tried it out on 4 different big data sets, and we were able to essentially find a solution that gave us insight into what's happening. And there are 2 things. I don't expect you to see or read anything here. This is a residual correlation after accounting for the rush stuff. But you still see a couple of light blue spots here on the off diagonal, and those indicate, I think particularly these here, that there's something going across that is not captured by this rush model, by this overall score. And this particular blue square indicates that there's dependency between the cases that is not accounted for. And this indicates, these tend to be the neutral items. This indicates that there are 2 processes going on. First of all, you try to do it right. You try to find the optimal items and actions. But then there's also a tendency to do a lot. These are all the neutral items. So those are the people, the do-gooders, or whatever I might call them. They just try to do more, which is not necessarily beneficial. They might give you an extra aspirin or some other medication that's not really needed, also prescribe some vitamins, just because they think more is better. And that showed up in the data that we wouldn't have found otherwise, other than looking at this kind of data. I will spare you the technical details, but we had a lot of fun with 2 summer students going through the theory that we got from the medical experts through the items, really looking closely at the data and then finding estimation methods and coming up with a model that is actually useful, that hasn't been used a lot in the past, but for specific kinds of tests it turned out to be useful. We were able to improve the reliability of the scoring, and in the end we also had better correlations with the multiple choice test that was also given at the same time. Again, for later reference, I will send the slides around if somebody's interested in this particular model. There's a lot on the Rush-Poisson count model. Margot Janssen has done a lot of stuff. Anna Döbler, Heinz Holling, Meredith, Rush has actually written about this. After all, it's the Rush-Poisson counts model. But it's a really nice application of a pretty straightforward model, 2 process data where you find additional strategies that you wouldn't have seen otherwise. Another little story in terms of time, I will probably drop the last piece, even though I would like to at least show the last slide, speaking about a wonderful experience with a student. So we had great success with her, writing a lot of papers. Her advisor and I were over the last 3 years, but again, that's my last slide. This is a professor from Technical University Dresden, and he was a really interesting guy. I don't think he was aware that he's actually collecting process data. I don't think he was aware that he's essentially producing data that every methodologist will salivate over. So he developed a test with his content experts. A little simulation you will recognize. This is a VW Golf. And he's in vocational education at the university. So he's training PhD students to get into vocational training education. So they train master mechanics to be able to train the next generation of mechanics. in applied colleges. He had very specific hypotheses around different types of process data, which he didn't call process data, but I will show you that they are, and how they are connected to certain solution strategies, how people solve a mechanical problem during education in this car mechatronics field. He actually had very specific ideas about how these different actions relate to strategies and how these strategies then should relate to actually getting the item right or not. His features were theory-based, so he didn't do some machine learning algorithm to extract features and then end up with some fancy stuff that nobody can understand. He actually had stuff that was as simple as, well, if you look at this problem, and you can do, again, all kinds of things. You can open whatever, a fault report, you can open a measurement instrument, you can open a logbook and the fuse box, you can look at whatever the error codes in the system. You can do all that stuff. And he connected each of the actions to a strategy. He would say, well, if you open up the expert system, you are more or less in the computer-based strategy. You might not have a good mental model of what's going on. You just read through what the error description says, where you should be looking. If you open up this measurement instrument, you might actually have a model-based strategy where you might have a mental representation of what should be going on in this mechanical system. And then finally, if you're just a novice, the best thing that can happen to you, you might have previous experience or not, and then you just mechanically follow what was good to do in the previous experience. If you know a little bit, then maybe you use the help or expert system and go through the error description. And then at the highest level, you more or less are in the mental model stage where you have a representation of what's going on. The process data was messy, as it always is, and I don't expect you to read this. It's also a little blurry. So those are essentially log files that say, well, student pressed this, student extracted that, student whatever checked this, student opened the expert system. He directly translated this into actions that represent a strategy and essentially implemented a nice little table that would say, if you do this, this, and that, then you use that strategy. And I've been working a lot on a methodology called diagnostic models or diagnostic classification models. And when I saw his work, I told him, look, you're presenting me everything that usually a test developer doesn't do. We have a grouping of actions, we have a grouping of things that you think are related to certain strategy types, and we can actually extract these strategy types based on the data you give me. So he gave me this little matrix, and just think about all these different categories are based on log file entries that he mapped to those. So he has this long list of pressing this button, opening the expert system, checking the fuse. And for each of these actions, he has a direct link to this relates to doing one of these things, opening a sensor diagram, a sensor circuit diagram, or looking at the diagram of the location, or opening the expert system and reading the instructions, etc. Doing a sensor test with this multiple, how do you call this, multi-thing instrument. Essentially the meter for testing resistance, etc. So he had all the building blocks together, and that was really the first case where I was seeing that the statistical models that everybody was so excited about were actually useful, because there was somebody who did all this work and went through theory-based defining strategies and then actually looking at the log files which would represent those strategies in terms of concrete actions. Then the rest was really pretty easy. We wrote a nice paper. I hope it's nice. And this model that I worked so hard for developing, and that usually never fits better than standard models, all of a sudden actually fits better. So this diagnostic model, in terms of fit indices, which I can't explain here in this short time, actually shows a smaller deviation value and shows better fit than all the standard models that you might want to try. So we have a better fit compared to standard models that people would usually throw at this type of data. We have different types of problems where we saw consistent results that had to do with the theory that he was all about. And in the end, we could even see strategy shift between simpler and more complex models. And just in terms of time, I don't know how it is. We should probably 10? Okay. Then I will go directly to the last section. So this is one of the poster cases, I would say, that really made my day back then when I was working with this person, because it really showed that somebody can think about process data in terms of giving you additional information, in terms of actually providing something that you couldn't just get based on do they get this item right or not. Okay, I will jump over all these wonderful slides and go back to another very fruitful collaboration. Steffi Pohl is a professor at Free University. Esther Ulic is her star student. So we worked on a Science Foundation funded project that tried to get together models for response times and models for response propensity. Response time models have been growing like crazy over the past 10 years. In every computer-based assessment, you get the time for each item on pretty much every item, even background data. Typically, you get a model developed by Wim van der Linden from Twente University, then later from CTB McGraw-Hill. So he developed a model around the log normal response time and an IRT combination. There are other ways to do this. You might have time-dependent items where you just have 60 seconds per item. You might have diffusion models, but we won't talk about these today. So this log normal IRT model is pretty predominant in many research studies. Missing data is a nuisance, and the problem is they have never been looked at together. So missing data have been modeled separately from response data, but the response time never came in. Then a couple of years back, we looked just empirically into response times for missing data and observed data. And omitted responses are in some ways also a response strategy. I get an easy way out of an item that I don't want to. If you look at international assessments, you might have kids from lower performing countries where you see in 40% of all responses, they don't do anything on constructed responses. So not responding is a response strategy in some strange ways. It's also a strategy that differentially takes time. So this little graph here shows the curve for non-response. So non-responses are extremely fast. Then the incorrect response sometimes has this kind of bimodal distribution. This could actually be sometimes stronger, where the fast incorrect responses look somewhat like omitted responses because they are probably guessing. And then the slower incorrect responses look a lot like correct responses in terms of timing because they're trying but not getting it right. So the incorrect responses are kind of a mix. The omitted responses tend to be fast. The correct responses tend to take longer, at least for somewhat harder models, harder items. So we had a lot of fun developing new models for that. So we essentially extended this Wim van der Linden model and assumed a parallel process between missing responses and observed responses. And this model alone just integrates those two different approaches. So you have the response propensity modeling as well as the missing data models. It's a pretty complex animal. I don't want to go into any details about estimating this, but modern Bayesian methods can help you there. So that was published just recently, but we went on to do a few intermediate models and finally came up with a model that we are really very excited about, which tries to integrate time use as well as missingness or omitted responses and test engagement if you just look at the research around test-taking motivation, you will see that this is an extremely important case, in particular for low-stakes assessments such as PISA, TIMSS, Pearls, etc. People don't really need those assessments, at least at the student level, because they don't gain anything from taking the assessment. At the school, district, and country level, that can be very different. But we try to expand the previous model just in terms of saying, well, we would like to have a measure of this engagement, and how can we get this? So we know the timing is very different between observed and unobserved responses, between guessing and trying. So we ended up with a pretty complex model that took incredibly only 2 months to develop, but then to estimate it was quite difficult. We integrated all kinds of fancy additional stuff, such as a higher order grade of membership model for guessing and omitted responses to measure test engagement. And I'm just showing it to you because, well, yeah, we've been successful publishing it, which is in itself not particularly important, but we've also been successful to attract interest in terms of having a validation study going on, where students do a self-report on how engaged they were, how much they were guessing, how important this test was for them. So here we have like a convergence between just psychometric model building that might or might not mean anything, and then something where students actually talk about how they solved the test. And I think that's a little bit of a missing link. This model itself can be estimated, but it's much more important then also to look at external criteria to see what those derived variables actually mean. It was only half of the model, so I have to say this here. So all the timing processes are parallel to this, because we know disengaged responses take shorter time. Disengaged responses or guessing or omitted responses tend to be also consistent over time. For that, we had this higher order model. Estimation was a challenge. So we are able to do this in Bayesian frameworks, but we want to extend it to a more frequentist framework that is then also suitable for something like full PISA data. And yeah, Esther was extremely successful in getting this stuff published. So she had 2 years of nothing. And then in the last year, she published 4 papers in pretty high-ranking journals. And after she graduated, we had to tell her that this will never happen again. So this is something that was probably your most successful year. Don't be depressed, because to get 4 papers in 4 really nice journals, that doesn't happen every year. And my little summary, I don't know whether you can read this up there. I really don't pretend to know all the answers, but I think we need to go beyond the exploration of process data and really go to some more theory-based, some more, what do we want from them? What kind of variables are we interested to extract? And machine learning is nice, but we also need to know what we are using it for. And I thought this little cartoon there with we just stir until the right algebra gives us the right results simply doesn't do it, because we simply have so much process data. So we need to focus on the right stuff. Thank you so much.